Straight wing. This is the basic wing that extends straight out from the fuselage with little to no sweep. You'll see it on trainers like the Cessna 172 and many small general aviation aircraft. Straight wings generate strong lift at low speeds because airflow moves directly across the wing. That makes takeoff shorter and landing slower and safer. They also stall more predictably, which is perfect for student pilots. The downside is drag. As speed increases, drag rises quickly, making straight wings inefficient for high-speed flight. That's why they're common on light aircraft, but rare on jetliners. Swept back wing. This wing angles backward from the fuselage and dominates commercial and military jet design. Aircraft like the Boeing 737 and Airbus A320 use swept wings to cruise efficiently near the speed of sound. Sweeping the wing delays the formation of shock waves and reduces compressibility drag at high speeds. That allows jets to fly around Mach 0.78 to 0.85 efficiently. However, swept wings reduce low-speed lift and can make stalls more complex, which is why jets rely on flaps, slats, and advanced flight controls during takeoff and landing. Forward swept wing. This wing angles forward instead of backward, giving the aircraft a unique appearance. The Grumman X-29 is the classic example. Forward sweep improves airflow over the wing during sharp maneuvers and increases agility. It also keeps the wingtips from stalling first, which improves control at high angles of attack. The major issue is structural twisting caused by aerodynamic forces. Without strong composite materials, the wing would literally twist itself apart. That's why forward swept wings are mostly experimental and rarely used in production aircraft. Delta wing. This triangular-shaped wing is commonly seen on supersonic aircraft like Concorde and many fighter jets. The large surface area and swept leading edge make it ideal for high-speed and supersonic flight. Delta wings are structurally strong and provide significant internal space for fuel storage. At high angles of attack, they create stable vortex lift, which helps maintain control at extreme speeds. However, they produce higher drag at low speeds and typically require higher landing speeds, meaning longer runways are necessary.
Tapered wing. This wing is wide at the root and gradually narrows toward the tip. Most modern airliners like the Boeing 787 use tapered wings because they provide a more efficient lift distribution across the span. This reduces induced drag and improves fuel economy. Tapered wings are lighter than rectangular wings and help reduce stress at the wingtips. The shape also helps control stall behavior, though designers must carefully balance taper ratios to avoid tip stalls. Elliptical wing. This wing forms a smooth oval shape from root to tip and was famously used on the Supermarine Spitfire. The elliptical design produces near-ideal lift distribution, minimizing induced drag and maximizing aerodynamic efficiency. In theory, it's one of the most efficient wing shapes possible. The problem is manufacturing complexity. The curved structure is difficult and expensive to build, which is why modern aircraft achieve similar efficiency using tapered wings instead. High wing. This configuration mounts the wing on top of the fuselage. It's common on utility aircraft like the Cessna Caravan and many cargo or bush planes. High wings improve downward visibility and provide excellent ground clearance, which is useful for rough or unprepared runways. They also create natural pendulum stability because the aircraft's weight hangs below the wing. This improves stability in flight. However, maintenance access can be more difficult, and aerodynamic efficiency may be slightly lower compared to low-wing jets. Low wing. This configuration attaches the wing near the bottom of the fuselage. Most commercial jets and high-performance aircraft use low wings. This setup allows landing gear to retract into the wing structure, saving space and improving aerodynamics. Low wings also provide better roll performance and are generally more aerodynamic at high speeds. However, they offer less ground clearance compared to high-wing designs.
Dihedral wing. This is when the wings angle slightly upward from the fuselage. Many passenger aircraft use dihedral to increase natural stability. If turbulence causes the plane to roll, the wing geometry creates restoring forces that help level it automatically. This makes the aircraft feel smoother and more stable during flight. Too much dihedral, however, can reduce roll responsiveness. Anhedral wing. This is the opposite of dihedral, with wings angled slightly downward. Fighter jets often use anhedral wings because they reduce natural stability and increase maneuverability. Less stability means the aircraft responds more quickly to pilot input. Modern fly-by-wire systems help control that reduced stability, making highly agile aircraft possible. Variable sweep wing. This wing can change its angle during flight. Aircraft like the F-14 Tomcat use this system to extend wings forward for takeoff and landing, then sweep them back for high-speed flight. This design combines good low-speed lift with high-speed efficiency. However, the mechanical systems required to move the wings add weight, complexity, and maintenance challenges. That's why variable sweep wings are rare today. So there you go. From simple straight wings to supersonic delta designs, every wing shape exists for a reason, balancing speed, lift, stability, fuel efficiency, and mission purpose. Some designs dominate commercial aviation, others belong to experimental or military aircraft. But each one represents a different solution to the same challenge: how to fly efficiently through the air. Which wing type do you find the most interesting? Share your thoughts in the comment section and make sure to subscribe to the channel.